All right, so in theory, you were practicing some applications of conic sections yesterday. These problems specifically out of the textbook. And just as a refresher, here are the answers for section 8.1, for section 8.2, and for section 8.3. Um, it looks like there were some questions that came in yesterday. I'm going to try to work those out for you. Um, First one, well, somebody asked for 59, but they didn't specify because there was a 59 in section 8.1 and there was also a 59 in section 8.2. So I guess we can do them both. Let's see here. This is a parabola problem. It's a parabolic shaped reflector within this flashlight, and what that's going to do is the signal. We want the light bulb to be at the signal source, and so it's going to reflect all through here. And because of the nature of a parabola, these are all going to come off parallel to that axis of symmetry, and it creates a really strong beam instead of a lot, beams of light going everywhere, and then we don't really get a sharp beam. If you have that parabolic nature, everything's coming off the same. That's going to be really helpful. So I'm going to go ahead and throw an axis in here. I'm going to make this easy on myself and center the vertex at 0, 0. So that's going to make life easier on me for sure. I don't have to worry about H and K. And because this parabola is horizontally orientated, that means it's a y squared parabola. So y squared equals 4px. Um, I just need one of these 2 points that would be on the parabola to solve for p, which tells me how far the that filament, that light source should be put, because we need it, we need it at the location of the focus. So I'll just grab this point right here, right? It's over 2 units because they told me the depth of the paraboloid is 2, and then the height is 3, because they told us that the entire diameter of this dish is 6, so half of that would be 3. So y is 3, x is 2, and it looks like 9/8. We're in centimeters here. So 9/8 centimeters is the distance that we need to be the from the vertex. That's where the focus would be, right in here. That's where we need to put that. All right. All right. The next one is problem 61, and it's another paraboloid problem. It says that the sports channel is using a parabolic microphone at a golf tournament. I gave you a little picture here, but it is really grainy. You can't even really see what this dude has. Here's a picture of a football game, but you can at least tell what the guy's holding there, and you can see it's basically a dish with a microphone that's positioned at the focus, and all of the sound that comes into here is gonna bounce right to the microphone, so it really amplifies what it's hearing. So that's in theory what this dude's holding here, and That's what allows you to hear the swing and the swoosh of the club and the click of the ball being hit. But anyway, let's see what they want. If one of the microphones has a parabolic surface generated by parabola, x squared equals 10y, then locate the focus. All right. Well, because it's an x squared parabola, it's going to be going up and down, even though it looks like he's holding it left and right. It doesn't matter. It still have the same dimensions, just in a different orientation. So x squared equals 4py. We need to solve for p, but we know that that 4p is equal to 10, right? Here's what we know. We know that the x squared and the y squared match up. The 10 has to be that value of 4p. And so I think all we need to do is set 4p equal to 10 and solve for p. And so we get 2.5. This is in, well, they didn't even tell us the units. So 2.5 units. They just wanted us to, I guess, give the point of this focus, maybe is what they wanted to. And 0, 2.5 would be the answer. So that's that one. So 59, 61, 53 is the next one. So here is an orbit problem. They start off by using a couple words that we didn't talk about in our notes, apogee and perigee. We did talk about aphelion and or aphelion, I guess is how you pronounce that, and perihelion, and those were based on helios, right, the sun. Well, we still see the same prefixes, apo, para. So apo is still going to mean far, para is still going to mean close, but this time we're talking about the Earth, because we're talking about the moon's orbit, which goes around the Earth. So the Earth will be at one of the foci of the ellipse, and the moon then, I don't think the moon's bigger than the Earth. I'm going to shrink it just a little bit. The moon will go around. Now, this is probably more elliptical than the moon's orbit, which is fairly circular. But that's kind of what the situation would be. Now, here's what they told us. They told us the apogee, which is the furthest distance. So that's the furthest it's ever going to be is this right here, a plus c, right? We could have looked up the formula that we had from the notes, but that's a plus c. We also have given to us the perigee, which is that longest distance, but then minus the c value, and all that's left is the short little distance that's the closest that will ever come to the moon. And so those two values create the apogee and perigee. Now, because they gave me both of those, I'm going to plug those numbers in. 252, 710 for the apogee, 22, 1463 for the perigee. And I'm going to treat it like a system of equations, two variables, two equations. I could either subtract these two, which would solve for c, or I could add these two, in which case the opposite c's would cancel. That's what I did. Okay, I added the two equations. I get 2a on the right and 474,173 on the left. And then dividing by 2, I get my value for a. Remember, we're pretty much looking for three things, or four things: a, b, c, and then the eccentricity, e. And we just found a. But once I find a, remember, I have two equations already that are based on a and c. So I can just plug a. It looks like I just plugged it into that first one. Now that I found it, right? Plunk, and I subtracted it to find C. So C is 15,623 miles. That's a pretty small amount, when you compare it to 252,000, which shows you that there's not a huge variation in the distance from the moon to the Earth at its furthest and closest points, but there is some. And you can tell the difference. When it's really close, the moon definitely looks larger, especially on the horizon. Now to find B, we're going to have to go to our favorite elliptical relationship, a squared minus b squared is equal to c squared. And we will plug in c value here and the a value here and square them and solve for b. And I'm not going to work that out because I know you guys know how to use the Pythagorean theorem. In this case, I guess it's Pythagorean relationship, but not the actual theorem. But anyway, this is what you would get for B. You can see that B and A are, oh geez, what is that? Maybe about 500 miles apart. It's not a tremendous difference. That's because the minor axis and major axis are fairly close due to the circular, um, circular nature of this elliptical orbit. Last thing we needed to do was just plug in C and A for the eccentricity. You get about 0.066. Now, it did ask us to interpret those values. Okay, we can do that. A is the distance from the moon to the center of its elliptical orbit, so that would be 237,086.5 miles. B would be the distance to its minor vertices, and that would be 236,571.162 miles. The C value is the distance from the center of the moon's orbit to the Earth, which is at one of the foci, which remains a constant 15,623.5 miles, right? And then finally, the eccentricity tells us how circular or elliptical this is. Remember, an eccentricity really close to 0 is pretty circular. An eccentricity pretty close to 1 is very, very long and irregular, very elliptical, very eccentric. And so 0.066 is definitely closer to 0 than it is to 1. All right, so 59. Okay, oh, our textbook is, notice this, Pluto was still a planet when our textbook came out, so wow. 59 also had ellipse problem, so I wasn't sure which one we wanted. I'll go ahead and do this one really quickly. Lithotripter, that's that medical machine you saw in the lecture yesterday, which is generated by a three-dimensional ellipse, basically an ellipsoid. And so it tells us where the major axes are. So let's go ahead and put those down. I knew this was horizontal because the major vertices were on the x-axis based on the points they gave me. And then one of the minor vertices is here. Okay. And so what they've basically given me is that A is 8 and B is 3.5. Now I know A squared minus B squared is C squared. And so I can just plug those in and do a little algebra, and C is about 7.194. So what are the coordinates of the foci? Well, plus and minus 7.1940 are where those foci would be. So that's how you do 59. Now, the last questions asked of me were for the hyperbolas, and we had a very long example at the end of the lecture, which dealt with rogue comets or interstellar comets, and 55 and 56 were both dealing with that. Now, I'm not going to do both of these because the problems are truly the same. Let's back here, check this out. Okay, if you kind of compare these word by word, they say the same thing. The only thing that's going to change is this number and this number, and 250 turns into 405. Other than that, these are the same problems. So I'm not going to do the same problem twice. If you know how to do, if you know how to do 50, what just happened there? If you know how to do 55, you'll know how to do 56. So I am going to go ahead and do 55 for you. And then if you were stuck on these, use this example of 55, which is going to be the same exact way I worked out the example in your notes on page 11, I believe. Use those two examples and work your way through 56. It's really using the same system of equations that I'm going to build here for you, okay? So here we go. A comet following a hyperbolic path around the sun has a perihelion of 120. Now, one thing that I will say here, let's do this. Here's the sun. Notice that it wants the sun to be on the positive x-axis. That's why I'm going to put it on the x-axis instead of the y-axis. Not a huge deal, but there's the sun. And then here is the path of the comet. The sun is at the focus, and the center, I'm going to put it 0, 0, so that H and K are non-factors in this problem. Try to make it simple, right? So this is kind of how this hyperbola would look to some degree. We don't have to be super perfect, okay? And I'll even throw a comment in there for you just to get this thing moving, okay? So here's what we know based on what we know about hyperbolas, all right? We know that the distance from, I'm going to go ahead and give us a vertex too, by the way. Loop. The distance from the center to the vertex is A. The distance from the center to the focus is C. So the perigee, or I'm sorry, perihelion, because this is with the sun, is going to be the larger distance, right? This is what I'm trying to solve for right here. This it's going to be the larger distance, C, minus the shorter distance, A, C minus A. Now, realize that this is actually, they did give us this, by the way. I'm going to go ahead and plug it in. It's 120 gigameters. Remember, a gigameter is like a billion meters. That's a lot. Notice that C minus A is the exact opposite of the one we were just using with the ellipses, because in the ellipses, A is further away than C. So we had to do A minus C. But for hyperbolas, the focus is further away from the vertex. C is larger than A, so C minus A. So the perihelion formula does switch depending on if we have a hyperbolic orbit like this problem or the more typical elliptical orbit like the planets and most comets have. Anyway, that's equation one. Okay, we're going to need three equations to solve this because I have three variables, A, B, and C. Now, this was the part that was just kind of a random fact. And in the lecture yesterday, I did show you where this comes from. Okay, but the statement is that when the sun is perpendicular to the focal axis of the orbit, so the comet comes through, boom, right here, right? And it's perpendicular through the focal width, half the focal width actually, to the sun's focal axis. The value there is 250 gigameters. So this is 250. Now the fact that I told you that was really important to keep in mind is that 250 is B squared over A. Okay. Now, like I said, I'll go back here in case you want to pause this again and not have to look back at the other video. After we did the example, I did a little mini algebraic proof. Y is the half the focal excess b squared over a. So you guys can follow this through if you want one more time on your own in case you accidentally missed yesterday's lecture. So you can just kind of like go through that, or you can go back and watch the full explanation. But it's just a fact you need to know. You just have to realize that that distance will always be b squared over a. So that's equation 2. Okay, that's equation 2 that we need to know. And then the third equation is the classic elliptical equation, which is just a squared plus b squared equals c squared. That's the third one. So I have 3 variables. I can't solve unless I only have 1 variable. But luckily with 3 equations, I can solve. Notice that the key here is going to be a, because I've got an a in both of these equations, but that's the only variable that is in both equations. So if I solve for c in terms of a and b in terms of a, I can substitute into our final equation down here and eliminate everything except for a's, and then I'm off and running on my solution. So that's what we're going to do. This equation is going to become c is equal to, I'm going to add a to the other side, a plus 120. So there's the first equation I'm going to use to substitute. This one, I'm just going to multiply by a, and I'm going to get 250a. So now that one's ready to substitute. Notice they're both in terms of a. So I'm going to be able to substitute those into this equation right here. And let's do it. So a squared stays as it is. B squared is going to become 250a. Notice I don't have to square that because I'm substituting b squared in for b squared. Okay, it's a direct equality. C is not. C is equal to a plus 120. So to get c squared, I'm going to have to square that. So I'm going to get a squared plus 250a is equal to, I'm going to have to FOIL this. Okay, if you forget to FOIL it, you're in big trouble. So I'm going to get a squared. I'm going to get 120a plus another 120a, which is 240a. And then finally, I'm going to get 120 times 120, which I believe is 14,400. Yeah, I think that's right. We'll find out if it isn't here soon enough. But looks good to me. So let's solve. The a squareds cancel, one on each side. I can subtract the 240a over, and I just get 10a, which means that the value of a is just going to be 1,440, right? So, and that's in gigameters, by the way. So we got a done. Now, once you get a done, the hard work is over because we have direct relationships to find b and c. In fact, c, remember, was a plus 120. So I can just say, oh yeah, c is a plus 120. So it's going to be 1560. And b squared is, got to scroll up a little bit here, 250a. So 250 times 1440. And so if I multiply 250 times 1440 and take the square root, I get, wow, nice, perfect square. They don't always work out as perfect square. Sometimes we have to approximate, but this one is. So 600 for B. Oops, it's kind of weird. I was just trying to put units in there. So now we have A, B, and C. The only thing we haven't found that it asked for was the eccentricity, which the eccentricity remains C over A. This should turn out to be a a value larger than 1 for hyperbolas. It should be larger than 1. C was 1560. And A was 120, I think. No, A, we see software down here. A was 1440. So, 12 goes into both of those, actually. That would be 13 over 12. So 13/12 would be the eccentricity. A little bit over 1, yeah. It's a decimal, by the way. That would be 1.083 if you wanted to write it as a decimal. The last thing it asks for is the coordinates for the center of the sun. And that's just going to be based on the C value, right? We found that the C value was 1,560 gigameters, so 1,560 positive x-axis is where that lives. So you can see it's always going to involve the same three equations: the perihelion equation, the half focal width equation, which is really kind of the one you got to just remember if you want to do one of these, b squared over a. Just one of those things you want to know, because I don't think you're going to do that long proof for it on a regular basis. And then, of course, finally, the classic hyperbola relationship between A, B, and C. So those are the questions that were asked last night. Hopefully this helps you. I could still do a couple more of these if people needed them done during our kind of tutor time tomorrow, 3 o'clock. I'm sure at 3 o'clock on a Friday before spring break, everybody's going to be super excited to meet. But if you have questions, you know that I will be here to help you out. Try 56 if you didn't get 55, because other than two different numbers, it's the same setup. You might not get those nice perfect squares for the values, but that's how it works. And remember, conic sections are things you should have learned in 4th grade, so this stuff should be easy for you, right? I'm just kidding. We'll talk to you tomorrow, or I guess later today. I'm losing track of time because I can't remember if it's past midnight or not. But anyway, peace.